not cylinders, we did cylinders, cones, and spheres. And spheres are my very, very favorite solid in the world. What do you see here? What do you see a sketch of? Y'all talk about this all the time. Hogwarts! Yes. Look how many cones are in that picture. Whoa! That's a lot of cones. So cones show up in the real world a lot in architecture. There we've got a cone. There's a example of traffic aids, and you use them in soccer and different sports. And you got a funnel. You can use it in mechanics, or you can use it in cooking, and then good old waffle cones that you can eat. So lots of cones in the real world. A cone is very similar to a pyramid. Cone is to pyramid as cylinder is to prism. A cone is just a pyramid with a circular base. A cylinder is just a prism with a circular base. You may draw this picture if you like. Of course, just like a pyramid, the height, the slant height, and the radius will cooperate to make a right triangle. So every time, if you know two of these, you can find the other one using good old Pythagorean theorem. Here are the cone formulas. These differ a tiny bit from your formula chart, so I'll talk about that. The lateral surface area is just pi times r times L. So it's not 2 pi RL, kind of like it was in a cylinder, 2 pi RH, because that surface area is kind of like half of the cylinder, the lateral surface area. Here's the net of a cone. So when you find the LA, you're finding this part of the cone. And when you find the SA, you're obviously finding this whole part of the cone. So the total surface area, you take the lateral surface area and you add in a circle. And then the volume works the same way a pyramid did with a prism. If you take a cone and a cylinder and they have the same base and they have the same height, then it would take 3 of these to fill 1 of these, 3 of them. So how do you find the volume of a cone? You find the volume of a cylinder and you divide it by 3. You can put 1/3 in front of that alternatively if you choose. All right, we're going to start off with simple, basic formula, and then we'll do a composite figure. So I gave you R, I gave you H. Please use your toolbox to find L. We'll go through this one quickly so we can spend longer on the cooler problems. I said use your toolbox to find L because I was saying Pythagorean theorem is like one of the tools in your toolbox. You've got 30, 60, 90, you've got trig, you've got different ways you can find missing sides. Sorry. What is it? Yes, slant height. It doesn't stand for length. It stands for slant height. So these are all centimeters. Please, please, while you're getting used to this, it is so easy to mess something up when you go to your calculator if you don't write it down first. So please write down the formula first until you're feeling really confident about it. Pi times the radius times the slant height. So what is the lateral surface area? You got it. 136 pi centimeters squared. And for the total surface area, you take the lateral surface area plus pi r squared. So you take the LA plus the B, pi r squared. Ends up being really pretty. What is it? Go ahead. Yep, 200 pi. Very good. So that was 136 pi plus 64 pi. Those are like terms. Since they both are in terms of pi, we are allowed to combine them as we add them and put them as one term. volume, pi r squared, so that's base, times height divided by 3. Area of the base times the height, not the slant height, divided by 3. 320 pi centimeters cubed. 320 pi centimeters cubed. All right, now let's try one that is a composite figure. Composite figure just means that I am creating a new solid out of 2 or more solids. This is a new solid, and I want you to find the surface area of this solid, not of these separately and add them together, because I have formed a new shape, and I only want the surface area of the new shape. I'm going to give you some time to think about this one before I teach you the strategy. Okay, let's talk strategy here. If we were finding the volume, it would be easy. Find the volume of this, find the volume of that, and add it together. Okay, thanks for that. But we're finding surface area. So our story is a little bit different here. Let's talk about what we would need to find. Let's work bottom up, okay? So, first, if we wanted to find this value, this area, what would that be? We're going to write down a strategy. Good. It would be the lateral surface area of the cone. So that's something we need to go find, the lateral surface area of the cone. Now let's go here. What would we need to find if we wanted to find this? Just what I'm touching. Just what I'm touching. Good. The lateral surface area of, you said prism, cylinder. Okay. Now, one last piece that I can touch. I can touch this. What is this called? The area of the circle. I'm going to call it big B, area of the base. Now, it could be the base of the cylinder or the base of the cone. It doesn't matter because they're one and the same. So we have 3 things to calculate. We have B, we have LA of a cylinder, and we have LA of a cone. See how we're breaking it down into different pieces and not just finding total surface area and adding them together. Okay? Very important. All right, let's start with B, one piece at a time. Area of the base, pi r squared, 25 pi. All right, now let's do the LA of a cylinder. Go to your formula chart. 2 pi r h, so 2 times pi times 5 times 6. All right, lateral surface area of a cone. There's our new one. So that equals pi r l. Oh no, we haven't had to find anything until now. We finally have to find something. We need to find the slant height, but of course it's a triple because we're just so nice. 5, 12, 13. Pythagorean theorem. Pi times the radius times the slant height. Are these like terms? Can we add them together? Yes, we can. Thank you, Alex. 150 pi square feet is the area on the surface of the figure. Let's move on to my favorite shape of all time. Spheres. All right. So, spheres are all over the place. Yes, Disney World, you got it, Epcot. Most every sport involves a sphere. Golf and baseball and tennis and soccer and racquetball and bowling and shot put. And think of how many spheres. What would we do without spheres? Seriously? Our planets are modeled off of a sphere-ish. This is really a pretty museum in New York. It's called the Hayden Sphere and Planetarium. It is a glass cube with a sphere inside. It's not an inscribed sphere because the sphere doesn't touch the glass, but it's pretty cool. That big golf ball thing in Dallas, okay. Oh, that's Reunion Tower. Reunion Tower, yeah, so cool. We're going to deal with Reunion Tower on our assessment. Okay, let's write down what a sphere is. It actually has its own definition. It is the set of all points in space that are a given distance from a given point. A given distance from the given point. Given distance is the radius, the given point is the center. So if you took a point and you decided that that is your center, it's usually called O, then all the points in all dimensions, not all dimensions, but all three dimensions, every point that's equidistant from that center forms your sphere. Set of points, given distance from a given point. Are there, Toby? I have not studied multi-dimensions. I don't know. I'm going to convince you a little bit more why spheres are my favorite and why they're the coolest 3D shape. So I like to be efficient. I like to spend the least amount of money possible or the least amount of time possible on something. And so spheres are the most efficient 3D solid. They have the largest volume possible for the smallest surface area. So when you blow up a balloon, it doesn't blow up into a cube. It doesn't blow up into a cone. A balloon blows up into a spherical shape because as the air expands, it's trying to get as big as it can get without popping. So as big as it can get, it expands in all directions from the center, and it forms a sphere. So that's the largest volume for the least amount of balloon material possible. When you blow a bubble, I blow bubbles all the time with my girls in the backyard. It also forms a sphere because it's trying to get as large as it can get without breaking that soap. Water droplets, they don't drop in cube form. They don't drop in cylinder form. A water droplet is nature's way of being the most efficient. What other spheres are in nature that nature creates, not man-made? The sun, the planets, okay, what else? Black holes, whoa, that's deep. Dewdrops, what else? Our eyeballs, seriously, yeah. Berries, circles are not an answer. I don't have many more. Pearls, nature creates pearls itself, and they're automatically spherical-ish. Got the berries, we got the flowers. Very cool. So spheres appear in nature, and nature even knows that they're the coolest shape, I think. Here are your formulas. The surface, wait a minute. Whoa, hold up. Why is there only two? Where's the lateral surface area? Did I just forget to type it? Very good, guys. If there is no base, there is no lateral surface area. Ooh, the golden snitch in Harry Potter! Ah! So cool. Anyways, so that's not a typo. There is no lateral surface area of a sphere. There's a total surface area, and there's, of course, a volume. 4 pi r squared, and do not ignore this. In the volume, you can write it like this if you want. It's 4/3 pi r. Be careful, we have never really cubed things in here. It's 4/3 pi r cubed because it's 3D, so you need r times r times r. You need all three r's. Here's our basic example where we just try out the formulas, and then we'll do some real-world examples. Surface area, 4 pi r squared. And I'll show a video to you on Monday about where that 4 comes from, or why the 4 is 4. It's pretty cool. It has to do with peeling oranges. Okay. 4 times pi, the radius happens to be 4. 4 pi 4 squared, final answer. (64 pi centimeters squared). All right, volume. Oops, I was about 2 3/4. It's 4/3 pi r cubed. 4/3 times, we're not going to press the pi button, but we need to press r to the third. So you need to press like the little caret button. I don't know, Alex. What do you get for volume? It should be pretty. Oh, never mind. Is it a... So not so pretty. 256 pi over 3. Or you can write it as 256 pi. And that's centimeters cubed, cubic centimeters. Never do we write the repeating decimal as our answer, because when you write that, you have to cut it off. And when you cut it off, you go from being exact to approximate. So please always math enter, and always enter your answer as a fraction. I would rather not a mixed fraction. I would rather the improper fraction, because they're more useful in math, I promise. Okay. The volume of a sphere is 288 pi cubic centimeters. Find the surface area of a sphere. This problem is very important because we're going to be doing something that we also haven't done yet in this class. I'll give you 1 minute to try it. All right, so we start this problem like any good work backwards problem. You write down the answer, quote unquote, the answer, because we know the volume, and we set it equal to the volume formula. So we've got volume equals volume. All right, we notice that the pi's cancel. We love when things cancel because it's less messy. How do we get rid of that 4/3? Good. You can divide by 4/3 if you want. Make sure you put it in parentheses. Or you can flip and multiply. You could multiply by 3/4. That's up to you. Pick one way and stick with it so you don't get confused. Okay, so you should get, what, 216? Yeah? Well, r cubed equals 216. How do you undo r cubed? Okay, if it's r squared, you undo it by square rooting. If it's r cubed, you undo it by... No. Cube rooting. You have to cube root both sides. It's kind of like square root, but it's with a power of 3. You need to cube root both sides. So, r equals, where is cube root on your graphing calculator? Press math. 4 is hidden inside the math menu. Math 4. See it? Do you see it? Math 4. Cube root of 216 is 6. Okay? Understand how to cube root? Math 4. So now it said to find the surface area, so we could do 4 pi r squared. (144 pi centimeters squared). Okay, last problem. Skip that one. I wanted to do a problem with a Hayden sphere. So this morning I just Googled it really quick. These are the real dimensions. The Hayden sphere is a glass cube with a sphere inside of it. So the diameter of that sphere is 87 feet. And the side length of the cube is 95 feet. I want to know how much empty space is there in the museum. How much empty space is there in the museum? Yeah, it's called the Hayden. Yeah, Hayden. You can look it up. So what do? What is our strategy here? You got it. Perfect. We're going to find the volume of both, and we're going to subtract. This is a volume question because when I say empty space, the space implies that we're not painting it. We want to know the actual air, the volume. Okay, so how do you find the volume of a cube? Do you know how to do that quickly? To find the area of a square, you do side squared. To find the volume of a cube, you do side cubed. Yeah, that's all there is to it. Your answer is going to be large. Don't be alarmed. It's real world, people. Real world is large. All right, now we need to find the volume of the sphere. Oh, no. Why did it have to be an odd number, right? Now, this is a real-world problem, so I want a real-world answer, so you press the pi button. Yes, you press the pi button. Or else you couldn't have subtracted them, Alex. You should have two separate answers if you didn't press pi. But we're going to press pi. We're going to get one answer. It's going to be approximate. It's not going to be exact. Nope, I didn't get either one of those. That's it, Asha. Good. The amount of space, airspace, in that museum is 512,584 cubic feet. Alrighty. Do your homework this weekend. It is so short. It's just a couple of cones and a few spheres on the back. It's short. We'll go over the answers on Monday.